Hello and welcome to Terahertz Imaging for Margin Assessment of Excised Breast Cancer Tumors with Dr. Magda El-Shinawi. I'm Mike Hamilton, your host for this IEEE Microwave Theory and Technique Society webcast, which is sponsored by our MTTS Education Committee. Before we start, I'll mention a few housekeeping items. First, this presentation will be archived. A recording should be posted approximately 24 hours after we finish the presentation. We'll send all registrants an email when the archived webinar goes up, so you can revisit it or share it with your colleagues. Second, we encourage questions. We'll wait till after the talk to answer them, but you can submit them at any time during the discussion. Enter your question in the Q&A box in the webcast window, and don't forget to click Submit. Third, some words about the interface. You can enlarge slides by clicking on the rectangle at the top right of the live slide window. You can also enter full screen mode if you desire. Refresh or reload the current web page if you encounter any problems. With regards to audio, if you're listening over your computer speakers, you can adjust the media player volume. You may also need to adjust your system's master volume. The icons at the bottom of the webinar window include a resource list. Clicking that link will start the process to download copies of the slides that will be presented today. Now let's introduce our speaker. Dr. Magda El-Shinawi is currently a professor of electrical engineering at the University of Arkansas. Her background is in electromagnetics, including theory, measurements, and computation. She received her PhD in 1991 from the University of Nebraska, where she was then a research associate at the Center for Electro-Optics from 1992 to 1994. She then spent several years each at the National Research Center in Cairo, Egypt, and then at the University of Illinois at Urbana-Champaign, followed by Northeastern University in Boston. She joined the University of Arkansas as an assistant professor in 2001, where she's currently a tenured professor. Her research interests include experimental terahertz imaging and spectroscopy, breast cancer imaging, image reconstruction algorithms, antenna design and measurements, computational electromagnetics, biopotentials, and biomagnetics of breast cancerous cells. Her current research focuses on terahertz imaging of breast cancer tumors, which is funded by NSF, NIH, and the state of Arkansas. She has published more than 228 papers in refereed journals and conference proceedings. Magda also teaches online courses for industry, as well as an open EM lab for undergraduate students, which is funded by the IEEE Antennas and Propagation Society. So now it's my pleasure to turn the virtual podium over to Dr. Magda El-Shinawi for terahertz imaging for margin assessment of excised breast cancer tumors. Magda?
Hello, everyone from the University of Arkansas in the United States. I'm very happy to present my research to you, and I welcome any questions. Thank you, Michael, for the nice introduction, and thanks to the IEEE MTT for inviting me. So we'll start with the title. As Michael said, this research is basically on using terahertz imaging for margin assessment. I will explain what do we mean by that. But I wanted to make it very clear from the start that we are not using terahertz for screening. We are not using terahertz to replace X-ray mammography for screening women, the annual screening process to detect the cancer. The whole terahertz imaging technique is for after the woman is diagnosed with breast cancer. So let me first introduce my team. We have a big team, as you can see on the screen. We have the upper row is the co-investigators. We started with Tyler, my former PhD student, who is now at Sandia. Dr. Rajaram, biomedical engineering, Dr. Wu, electrical engineering, statistical methods, and Dr. Bailey, the pathologist at Oklahoma State University. And then all our students, Nagma, Chris, Tani, Paula, and Egliana, all are between electrical engineering and biomedical engineering. So with this big team, I really appreciate all their help, and all the work is teamwork, so I give them the credit more than I give myself. So I would like to acknowledge the sponsor, because usually at the end we forget the sponsor. So this work is currently funded by two sponsors, the NIH, which is National Institute of Health, and also by the National Science Foundation. And we have the system of terahertz imaging and spectroscopy that was funded through a grant, Major Research and Instrumentation, MRI, from the National Science Foundation. So I appreciate their funding, and without this funding, we cannot do the research. I know that most of you know about terahertz frequency range, but I wanted to make it more clear that the terahertz frequency range is between the microwave and the millimeter wave on the left of the terahertz, and the upper frequency, which is the infrared and the visible light on the right. So the terahertz is in between, and this is a frequency band that was not has been used recently only to try to find the niche applications that only terahertz can do, and can do better than the other bands. So this is where we come in this research. So this is a problem we are trying to solve. Again, we are not screening the breast. Terahertz, as you know, is very high frequency. It cannot penetrate the skin of the person, or cannot see any tumors inside the breast. But what we are looking for is to look at the surgical margin. What do we mean by that? When the woman is diagnosed with breast cancer, she has two options. Mastectomy, which means that the surgeon will remove the whole breast, or lumpectomy, where the surgeon will decide to remove partial part of the breast, very small part, depends on the size of the tumor, and that's what we call lumpectomy. All our research is based on the lumpectomy surgery, because once the surgeon is started to do the lumpectomy, and he will remove the lump based on the X-ray mammography of the patient. But the surgeon, and no one actually with your eyes, you cannot see if you are removing all the cancer, or are you the surgeon is leaving cancer behind in the breast. So the sketch on the right of the slide, the upper one, where the darker cells we call cancer cells, the red ones, and the light pink one we call healthy cells. So this is what we call a negative margin, meaning the lump will be removed with no cancer on the edges of the surgery. On the lower one, we call it positive margin, where the cancer reaches the boundary. The positive margin is very dangerous, because if the patient has did lumpectomy and there is positive margin, this means that the cancer will reoccur in the same breast, in the same location, because not all cancerous cells were removed. And this is what we are coming here using terahertz. So, of course, once the lump is removed, the surgeon will send it to the pathologist. The pathologist, it's a lab, so they will put all the tissues there to be examined whenever they can. But this process takes 2 to 3 weeks in many cases, because those labs are so busy. So now, after 2 or 3 weeks, the surgeon can call the patient and ask her to come back. Why? Because she has to do a second surgery to remove the remaining of cancer, because the pathologist said that she has cancer, or she has positive margins. So the margins are not clear. So, and that's why she will do another surgery. And this usually occurs 20 to 40% of the cases of lumpectomy. And if the cancer stays there, it will cause another maybe a mastectomy later on. So, of course, in the sketch, things look clear and red and pink. But if you go to the actual tumor, when it is removed from the breast, this is in the figure on the right. So the lower one is the surgery. So this is the cavity, the surgical cavity, where the piece of the tissue was removed, which is the upper one. If you look at the upper one, you cannot see anything. You see blood, you see all the tissues with your eyes, they look the same. So what we wanted to do is to put this tissue, the excised tissue, on the terahertz imager, and try to distinguish between, are we having any cancerous cells on the surface of this tissue, or on the surface of the tissue we only see healthy, and which what the surgeon wants to see. And we wanted our goal, eventually, we wanted to go to the, put the imager inside the operation room and do this in few minutes while the patient is still in the operation room. That's our goal. So before we can go to do a clinical trials, we have to prove the concept, and we have to solve all the challenges that we face, as I'm going to discuss here. So we have now, what do they use now in the hospital? And I visited the hospital here, the local hospital in Arkansas, and they use X-ray imaging. So the image on the bottom, this is X-ray from a specimen. So a patient did the lumpectomy, and the surgeon, there is an X-ray machine, small one, inside the surgery suite, and they took the images trying to see if the margins are clear or not. The surgeon himself told me that it is very hard to see anything in X-ray films. It's very difficult. So also, some hospitals use the computer tomography, and we gave one of our samples to the Dr. Bang, and he did the image using computer tomography. Also, it is very hard to see even what was cancer, what was not cancer. So definitely there is a need to for another technology to be able to see the margins of the tissue fast and as much as accurate as possible inside the operation room. The surgery takes a certain number of time in the operation room. The medical scientists and the surgeons, they do not want to increase this time. So we have to get in and out very quickly. So this is our goal, to go to the hospital, but now I'm showing you in this slide our terahertz system and the spectroscopy at the University of Arkansas. The photo on the left has the system. It looks big. This all funded by National Science Foundation. It costs around $600,000. So we have two scanners. One, what we call core, like when you see this red arrow, this is the core scanner. I will explain more about it in a second. And another one, in the core scanner, everything inside that box. In the right of the image, we have what we call gantry scanner, gantry system. It does scan bigger samples. The core scanner, we use it for cancer tissue because the scanning window is around 2 centimeter by 2 centimeter. So quick review of the terahertz system. The source is a femtosecond laser, 800 nanometer wavelength. It does hit the antenna, which is like a bow tie antenna or dipole antenna on semiconductor substrate. And the antenna itself is biased with a certain voltage. So the antenna will convert the laser from 800 nanometer wavelengths to terahertz signal in the time domain. It's a signal pulse. And there's some bunch of mirrors, as you can see, the blue lines will direct the signal to the sample. In this case, it's a reflection mode. So the signal will hit the sample and reflect it back. And some mirrors will direct it to the receiver antenna. Part of the laser will also excite the receiving antenna or the detector, and everything is connected to a computer, so everyone can see what we are measuring, either spectroscopy or image and so on. The system output power is almost 1 microwatt, and if some of you, I'm sure they know that this is low, and although it is adequate for tissue because it doesn't harm the tissue, doesn't damage the tissue, but for other applications, a hot topic is to increase the output power of terahertz antennas. But this is a different topic. Now, the signal coming from the terahertz signal looks like the two figures at the bottom of the slide. We have a pulse system here. And then in the frequency domain, as you can see the spectrum, it goes up to 4 terahertz. Of course, the system noise increases at the higher frequency, and it depends on your application. Some application you won't see much of the noise. Other application, when the tissue is, or the sample is a tissue which is very absorbing or attenuating, you see the noise earlier at earlier frequency. So here I'm showing all the modules or the sample holders that we use for the imaging or for the spectroscopy. So we have a window here on the left, what we call reflection module. We put the tissue and we use a reflection module, like the terahertz will excite the tissue and then will reflect back from the tissue to the detector, or transmission where the terahertz will go through the tissue, or in the gantry system if we have say big sample which is not related to cancer, of course. Now for the spectroscopy, which is how to measure the electrical property of the sample, this is only one point, so you either you have transmission or at room temperature, or also transmission but at low temperature for up to 4K using liquid helium, or you can heat the sample if you want to higher temperature if you want to kind of analyze the effect of heat on the spectroscopy. For the cancer, we use the reflection module imaging, the transmission module imaging, and the transmission module spectroscopy at room temperature. So now this is the core system. If you open the top, so we look here on the right, we see the compartment where we put the sample, and you can see the receiver box, but still we cannot receive the antenna, and the emitter box here. So in this compartment, to get rid of the humidity in the air, and which the water has very strong signals in the spectroscopy or the spectrum of the terahertz. So we remove the water by purging this compartment using nitrogen gas connected to the system. So now the laser comes here, and then it goes to certain mirrors here. It goes to the antenna, the transmitter, the emitter, or the receiver, and to do its job. Also, we take the laser through fiber optics to the gantry system if we want to do bigger samples. So this means that we have one laser source and 4 antennas, 2 in the core and 2 in the gantry. So now this is the gantry antenna. We can see the antennas because it is up in the air, so we can see. So you can see also some mirrors here, and the fiber optics carrying the laser coming on the left, and then you see the antenna. It's very small, and then between the transmitter or the emitter and the receiver, whatever you put here in between, reflection mode or transmission mode. This slide is important if we want to look at the polarization of the terahertz signal. I will talk about it in another slide. So okay, so now here in this presentation, I'm focused on freshly excised breast tumors, because this is the actual application, and this is where we want to have how many sources of freshly excised we have 3 sources. So we have, of course, the main source is human tumors. If we can get human tumors as much as we can, this will make our life much easier. But obtaining human tumors, and we are outside the hospital, is very challenging because the hospital has rules and regulations. So we buy our human tumors from biobanks. So we buy it and they ship it to us within a few hours of excision overnight. So this is the best we can do with human tumors. Or we can have animal models, and in this research we tested 2 animal models. One is the xenograft. Those are mouse that you have to inject with cancerous cells and wait until the tumor grows. So, or transgenic mice, and those are spontaneous, meaning the DNA were kind of engineered such that they produce tumors spontaneously. You don't have to inject them. Or phantom model, and this is also something we need to use because 1 and 2, human and animals, they are expensive. Phantom model are very cheap, and if you want to test some algorithm or some nanoparticles or something, you can use the phantom. Okay, here is the procedure of our imaging. Once we have the fresh tissue, as I put on the left, once we receive it, we image the fresh tissue immediately. And then we put it in formalin and we send it to Oklahoma State University for Dr. Bailey to do the histopathology. And then he will put the histopathology. Basically, they take all the, there is no blood, there is no fluid. They take the actual tissue and embed it in paraffin block. So we get the FFBE, which is formalin fixed paraffin embedded tissue block. So these are very dry, and it's a block, like 2 centimeter by 2 centimeter, and maybe half a centimeter. And then he himself, the pathologist, will take a very thin slide from the blood and to do and send it to us. So once the pathologist sends us the blood and his image of the H&E, which is a stain, this is the standard pathology image. So we have 3 images. Our job is to analyze the images of the terahertz with respect to the pathology image. And we also looked at the FFPE and compare it with the fresh. So kind of you have a fresh, you have a dried tissue, and then you have the pathology. Everything in the imaging system based on scanner, meaning we have a stepper motor, so we can pick up the signal at each single pixel from the tissue, and we can have the choice of a step size of 500 micron to 50 micron. Of course, 50 micron takes more time, but in general we use a 200 micrometer as a step size. So now for the first thing, the human breast cancer. So the biobank we are using called the National Disease Research Interchange, NDRI. It's very famous in the United States. So you contact them, they send you what you need upon setting up a protocol. So we follow the protocol. They send us a tissue embedded in this solution, the Bico modified Eagle medium, DMEM, and we tested this solution. It has no effect on the terahertz signal. It does not attenuate it. It does not disturb the signal in any way. So we know it is a safe solution. But this solution keeps the tissues fresh until we receive it. So every time we do fresh tissue, we we receive the tissue within 24 hours of the operation, and then of course once we do the fresh tissue, we send it to Dr. Bailey to do the histopathology. So here in this figure, I'm showing the fresh tissue, and then if we want to analyze and get the electrical properties of some pieces of the tissue, we take small pieces and we put it in a capsule called the liquid holder on the bottom left. And the remaining, which is the main piece of the fresh tissue, we put it on the imager and we do imaging, scanning, so point by point. For the spectroscopy, we only do 1 point to get the electrical properties. So here is what happens. When we have a fresh tissue, it has blood, although we try to dry this blood as much as we can. So we have to put it between 2 polystyrene slides. Polystyrene material does not affect the terahertz. It does not attenuate it. It is very close to air, so we are safe. Also, we save the signal. So in this figure here on the left, the terahertz signal comes from below, hits the polystyrene first, and then the tissue, and comes back to the detector. In the sketch in the lower part of the slide, as you can see, of course, the first signal comes from the air polystyrene, but this signal is not important to us. So if you look at the 2 signals on the right, so the one on the left here, the signal, you have a polystyrene signal, the first one, and then the tissue, right? And then what we do is we can control the time window of the system, and we cut the polystyrene, which is the air polystyrene, because this signal doesn't carry the information. It is the air polystyrene. All the information is between the polystyrene and the tissue, the second interface, and we focus on it. We focus on this tissue to make it as large as we can, as strong as we can. Our problem with the fresh tissue, and every researcher, is this fluid that's going around the tissue, and we try to dry it as much as we can. Sometimes we have air bubbles in the tissue, but it appears in the image, but we don't have anything to do. There is nothing you can do about it. So here is the breast tissue. The figure on the on the left is the photograph. We put the fibrous, which is the healthy tissue, cancer, blood, fat, and so on. This all information we get it from the pathology. The figure on the right is the terahertz. So we have the fresh image. Sorry. And we have, as you can see, that this is a frequency domain, and we collected data at several frequencies. Everything in the time domain, you go to the frequency domain, you pick up your frequencies, and you add all the frequencies, and everything we do, every sample, we have to normalize it with a reference to get rid of the, or to help with the phase, actually, of the slide. So in this image on the right, we did not dry the blood, and so you can see the blood is very high intensity, because this is very conducting material. So what happens that we have, we learned our lesson after that. So if you are doing any fresh tissue, please dry the tissue before you put it on the imager. So now this is a FFBE, the tissue that the blood, the pathology sends us to us. So on the left, the pathology image itself. On the right is our terahertz image without the blood or anything. Everything is dry. So you can see a correlation, a very good correlation. The cancer appears, the fibro, the fat. Always the fat has a very low intensity compared to the cancer, and the fibro is kind of in between. So we learned our lesson, and after that we started to dry our fresh tissue before we put it on the scanner. So this is another sample, and you can see on the left the how heterogeneous is the breast cancer. So it has cancer, it has fat, fibrous. Fibrous, again, is the healthy tissue that we really would like to see the difference between fibrous and the cancer. You do not want to cut more fibrous than you need, or less cancer than what you should. The fat is always very clear. It appears on the terahertz on the right. It appears as a dark blue because the intensity is low, while the fibrous and the cancer, they are differentiated, as you can see here on the terahertz image. So now we go to the pathology and versus the dried or the block image of terahertz. Again, because we don't have any fluids on the right image, so everything is correlated, highly correlated to the pathology, cancer with cancer, fat with fat, and the fibrous and so on. So now, if we want to analyze what is the properties of each pixel, so what we need to do is we have the measurements. So how would you extract the refractive index and absorption coefficient of any of these tissue types that we have seen? We've seen cancer, we've seen fat, we've seen fibrous, and it's important to understand the electrical properties. After all, terahertz is electromagnetic method. So if, for example, this is a transmission model, so if you have your slide, which is what I call region 2, and the sample, which is the pink one, we call it region 3. So you have your transmission model, on the left is the source. So you have your incident going through the slide and then through the tissue to be received at the detector on the right side. So of course this is a multi-layer model, air, slide, tissue, air. And if this is the model that you are putting your tissue on, then this can be derived straightforward from multi-layer flat tissue, flat model. And then the idea is, okay, we have the measurements and we have the model. So we can assume certain electrical properties. The algorithm will assume several of them, and we pick up the ones that minimize the error between the measurements and the model. So this is a box that I put at the bottom of the slide. So your measurements is time domain. You go to frequency domain. You have magnitude and phase. Then you have measurements and you have the model, and you minimize the error between them. And then this is how you retrieve your n and alpha. If you are in the reflection mode, like in this scenario here, so you have the tissue on top of the slide, so and you're coming from the left, but in the system that we have in the reflection mode, it comes at oblique angle of 30 degrees. So here I put the vertical polarization, and I will talk about that in a second. And then you send and receive from the same side. So the incident with the emitter, the reflection, you receive it at the detector. So what we have here is a model. Also, you can derive it. It's straightforward. And then you go back to the error algorithms that minimize the error between measurements and this model, if you are using the reflection model. So what is the polarization of the system? We actually do not know, because the system has a very complicated system of mirrors. So by the time the signal is emitted from the emitter until it reaches the sample, we lose the polarization because of the mirrors, several mirrors. So what we did a simple experiment. We got an acrylic plate, and we know that we have hybridized polarization, meaning we have a mix from between TE and TM models. So we with using the angle psi. So if psi is 0, your terahertz signal is TE. If psi is 90, your terahertz signal is TM mode, which is horizontal and vertical. So what we did the changes psi in the model, and we did several calculations, and we compared it with the black curve here, which is the measurements. And we found at the closest angle psi that the system provides is at 60. So we know that our terahertz signal in the reflection model is a mix between TE and TM modes with the angle 60 degrees. So this is another human breast sample. So this sample is very unique because if you can see, look at the cancer is majority of the sample surrounded by fat and a little bit of collagen, which is healthy tissue. And look at the terahertz image. It is perfectly compatible with the pathology. But now, since I can use the model and get the N and the alpha at each pixel, I was able to produce another two images, what we call alpha image, which is the absorption coefficient image, and the N image, which is the refractive index image at each pixel. On the plots on the right, we have at 1 point, 1 and 2, these points on the image. So we got at 1 point using spectroscopy, we calculated from the measurements, we calculated the reflection index, refractive index N versus frequency, and also for the alpha. We compared our results with a published result by Ashworth, which was in 09. He used at one single point, and he got the black curve here. So the results are compatible, not necessarily on top of each other. We have 2 points here. He has 22 patients. So we are working on producing more data here. Now, we move to the animal model. So we use 2 animals in our research. One animal, xenograft. As I said, you have to inject with some cancerous cells and grow a tumor, so this takes time. Also, you have to feed the mouse to become fat, because those are very small size mouse. Or the transgenic, which are very expensive, by the way, it's almost $300, but they produce several tumors without doing anything. You just keep them until you see the tumors, and then you excise the tumor and look at the freshly excised tumors. So in the xenograft here, this is what we do. We take excise the bulk tissue, and then we, because it's big actually for the scanner, so we divide it by 2. So each tumor gave us 2 sections, section A and section B. So now let us look at the results from the xenograft mouse 5. We had almost 14 mouse. So if you look at the pathology, section A in the left and section B, both of them in the left, you only see 2 regions on those tumors, fat and cancer. The skin really is not part of the tissue, because the tumor, breast tumor doesn't have a skin. Now, the images in the middle are for a terahertz image. So you can see very compatible with the pathology, 1-on-1. Cancer appears red, high intensity. Fat appears blue, low intensity. And now when we get the block, the FFPE block, we had this new images here, what we call the fixed image or fixed tissue image. Also, the cancer and the fat are very distinguished. So our goal, of course, is the fresh. They are very distinguished. Why? Because there are only 2 regions. Another example here, we have the photograph, and then we did fresh and the pathology and the time domain or the fixed tissue. there is no problem at all with the xenograft, but the problem is it is not really compatible with the human tissue. The human tissue is very heterogeneous. So here we moved to the transgenic mice tumor. So I'm showing here two figures for you to see the difference. The transgenic is very heterogeneous. The figure on the left, you can see all kinds of tissue regions inside the tumor, very aggressive tumor in the transgenic, and the xenograft is only two regions. So to get closer to human tissue, use transgenic because it has more tissues. At least that was the idea. So here, if we look at the photograph, and then we look at the terahertz image, the fresh, which is basically we put whatever was in the photograph on the imager. So now how to compare it with the pathology here in this slide. This is the blood. So in the blood, everything is more clear, and you can compare it with the pathology better because the pathology and the fixed FFAB blood is taken from the same surface. So they are more compatible with each other. So now you can see how heterogeneous is this tumor, cancer, muscle, fibrous, fat, all inside the tumor compared with the xenograft, the first animal model. Another example, this case is cancer on the left and cancer in fat on the right. And the fresh tissue here is showing very good result with the pathology of this transgenic mouse. Now we wanted to look at certain pages, certain points on the tissue to see what exactly, like what is point 1, point 2 that I marked here. And so we want to what we call high power pathology. The high power pathology is almost 100x like magnification. So we look at each point like cancer, cancer in fat, and cancer in glandular secretion, fibro, and so on. And we plotted the terahertz signal at each point. And as you can see the figure on the left, that these signals are shifted. There is a shift between each region, and this is because that each region has different refractive index n, and as a result is different velocity. So the tissue arrives at different velocities or at different times. So this gives us some idea about what are we dealing with here. Now the third one is the phantom. The phantom is very cheap. So what we put here, we colored the phantom. This phantom is made of water, oil, surfactant, agar, and so on. So we some powder, we call it TX151 powder. We have a recipe how much from each material we put together, and at the end we wanted the fiber to have the same electrical property as the fresh tissue. So if you look at the plots on the right, so all the solid curves are the spectroscopy of N versus frequency of our phantom, or the dashed is from the literature, the Ashworth paper, which is, we put it here in the slide at the bottom. So for the N and the alpha, the electrical properties, as you can see, very close. The solid and dashed lines are very close, almost on top of each other. Our goal from this fibro fat IDC, which is the red one, we colored with colored. This color do not affect also the terahertz signal, just for our eyes to see. This will eliminate the many of the expenses that if we wanted to create a model, a tumor model, such that we can use it in some experiments, right? Before we get to the tissue, because the tissue is expensive, either human or animal. So we had the 3D printed model here. So we look at the pathology, and then we create a 3D printer model, and then we fill this spaces with the material, like fibro and IDC, which IDC is the infiltrating ductal carcinoma. And on the figures on the right, another model. So we picked up this model also, and we created the 3D model at the bottom here, what we call the phantom tumor. So we can use these models to do some imaging until we know what we're doing, and then you go and buy those tissues because they're expensive. Now, everything we mentioned so far was when we say our results compare with pathology, was qualitative. Meaning we look at the pathology image, we look at the terahertz image, and we can see the cancer approximately in the same spot and the fat and so on. But we wanted to do quantitative assessment of the terahertz imaging, so we had to do some modeling, statistical signal processing work. So what is the problem here? As I said, for each tissue we have 3 images. The top one here on the right is the fresh. The one in the middle is the pathology. The one at the bottom is the blood tissue, also terahertz. The blood and the pathology, there is no deformation, so they almost at the same surface. And so there is no problem except that the pathology has a huge number of pixels because this is optical. But the terahertz has much lower because this is a lower frequency. The problem with the fresh, like at the top image and the pathology, there is a deformation happens during the histopathology. So we have the tissue, we put it on formalin, and then the formalin affects the shape of the tissue, and by the time we produce the pathology image, they look, even the shape is different. So we had to do some work here to do the quantitative. This work involved 2 things: classifier, so we can see in the terahertz image which pixel belongs to what type. Is it cancer? Is it fat? And then we compare it with the measurements. And now how to compare fresh tissue with pathology if the deformation occurred, they look different, the shape oriented different, and also the number of pixels is completely different. So quickly I will go through the classifier. So far we use the unsupervised Bayesian learning algorithm, where we start with the intensity of the terahertz signal at each pixel. We know that. And then the algorithm will do 2 things. Number 1, learning the model parameters. So the model is like, we have to decide what model. This F function, it's a conditional probability function. And then we say, okay, it's a Gaussian or T distribution or whatever we decide. And then we, in the learning, in the algorithm, will give us the parameters, meaning the mean and the standard deviation, and what distribution, what pixel belong to what. And then we estimate the posterior probability based on the Markov chain Monte Carlo algorithm. And then we make a decision. What is the decision? This ice pixel in the image belongs to the GIF category, meaning this ice pixel, is it cancer or is it fat or is it fibrous or what? So again, to continue this model, we start with the intensity, which is something we know. Then the pixel, that's something we don't know, that we would like to know what does each pixel belong to what category. And then the prior probability, it's unknown, but we have to assume some probability, and we go with it and we compare between probability assumptions. And then the algorithm will give us the distribution and the parameters like standard deviation and so on. What we're looking for, like this plot at the bottom, we're looking for, like here, we have a distribution of probability distribution of the fat, the red, very independent from the cancer. They do not overlap. And that's what we were hoping to see in all our images. Excuse me. So now here, how to do the mesh morphing. We start with the pathology, like in the left side, and then we do a mask like below it, right? And then we go to the look at the terahertz image, the shape, and we try to align the pathology as a mask that we did with the shape. We only use the exterior of the tissue. We do not use any information from inside, and we repeat this process until the pathology shape and the number of pixels under the matrix creation looks exactly like from the exterior, looks exactly like the terahertz, and the number of pixels are the same, so we can compare pixel to pixel. So here's some results of this. So we have here a xenograft which has only 2 regions, as we discussed, fat and the cancer, And then we have, so here is a pathology, then the morphic pathology that we use in the comparison. And then our terahertz image, this is a fresh tissue. And then the model will give me, based on the statistics, what is the probability that certain pixel will belong to cancer or fat. So, and then we do the RAC, which is a RAC curve is the true positive versus false positive. So if you look at the RAC here, the fresh cancer and the fat, the blue and the solid lines, they are not as good as when we did the fixed tissue, which is the dashed line. Although here in the two regions we had two probability functions, they are not overlapping, and this is very important because once you go to three regions here, this case has some muscle. So we have three regions, and so again we start with the pathology, and then a second one is the morphic pathology, which has the same size and shape of the terahertz tissue. And then we here we tested two distribution, one Gaussian, one T distribution. It did not really make any difference, or very little difference in the RAC curve, which is at the bottom of this slide. So if you look, all the solid curves are for the Gaussian, or the dashed curves are for the T distribution. They are almost very close. But here, if you look at the probability distribution, you see that we have cancer, and the cancer is blue and the fat is red. The probability overlap, which means that the model or the algorithm could not differentiate well the muscle and the cancer, right? So the cancer and the fat, because the presence of muscle really ruined the algorithm, because the muscle and the cancer, they have very close electrical properties. So this is a challenge, and we are working on how to improve the classifier if we have three regions. With this, I would like to conclude my talks. We have used three types of tissue, human, animal, and phantom. We have to use what we can get our hands on, because the human tissue are very hard to get. Even if you buy it, they don't send you a tissue every week. They send you a tissue every month or 2 months. So we have to use the animal to compensate for this shortage of tissue. Now, the terahertz showed very good correlation with pathology. For fixed tissue means the blood tissue, where there is no fluids, no blood, no nothing, except the tissue itself, and the images are very good. The challenge that we are working on now is the fresh tissue. Between presence of, sometimes we put the tumor on the imager, and what happens is that the tumor keeps producing or emitting blood, although we dried it. So sometimes it's very dangerous, it's very uneasy, not dangerous, uneasy to remove all the blood. The blood is very conductive for terahertz. It will reflect very highly similar to the cancer, and that ruins the image. So now sometimes we have bubbles, air bubbles in the tissue. When we put the tissue on the slide, it doesn't stick 100%. There are some air bubbles there. Now the other challenge that our pathology and the fresh tissue are not taken exactly at the same slide, but at the same surface, but at different, because the deformation that occurs during the histopathology. So we have to find a way to do this. But so far, histopathology is our main reference, but we have to compensate for that change. Now the classifier, when we do two regions, is okay. 3 regions, it did not work as well, and we're working on how to improve this. By this, I conclude my talk by thanking everyone who listened to my presentation. And this is our website. These are the references we used here in this work. And this our website, we always put the PDF of every single journal paper we publish, so for your convenience if you want to download it. And by this, I conclude my talk, and I welcome any questions from you about this research. Thank you very much.
That's great. Thank you, Magda. That was a really interesting talk, and a lot of challenges there. It is time for our question and answer session right now. So before we start, remember that you can still submit questions through the Q&A panel, but we'll try to get a few questions answered here. Okay, here's the first question. So about how long do the measurements take?
So when we use that 200 micrometers motor stepper, it takes maybe more than 20 minutes, sometimes 30 minutes. If we use the 400 microns, it takes like 10 minutes. So usually we use the 400 micron first, the stepper motor, just to see what are the boundaries, what are we looking for, and then we go to the 200 steps to see more of the regions.
Okay. Okay. There's a couple of questions here about stimulation in the time domain, reconstruction in the frequency domain. Could you just provide some comments and clarification on how, why that approach is taken?
Right. So the system produces time domain. So the signal we receive in the detector is time domain. The model, this is very simple model. This multi-layer model is a frequency domain. So of course you can two things you have to pay attention to. This model is simple because it's all the interfaces are flat. That's why we put the tissue between the two slides to make the surface flat. But if we move to the construction of the properties N and alpha using the model, the flat model, and on the extent that we go to the frequency domain, which means that I just do the first Fourier transform of the signal, it's still very simple. It's very, very simple model. If you want to stay in the time domain and do the reconstruction in the time domain, it is very possible. You have we have the measurements, and there are many inverse problems in the time domain can be used. So it's not like we don't have to use the frequency domain. So we can use the time domain, but we did not do it. We feel like the flat interfaces model is very simple. In the future, we may move to other inverse problem algorithms to do so.
Okay, that's great. So how about some comments on terahertz being a high frequency and the penetration depth associated with that and the challenges
right.
that you addressed that?
We don't really, yes, when we started, we thought that we have to deal with the penetration depth. The penetration depth of terahertz, as known, is not much, like a few hundred microns, so it doesn't penetrate. But because there was this one. So this one here, I did not read it when I was introducing the problem. The American Society for Radiation Oncology, they posted the guidelines. The guidelines is that if you have any cancerous traces of cancer on the surface, that's good enough to say the margins are negative or positive. You do not have to go inside. Remember, this is excised tumors. So whatever is inside, we know that it is cancer. We only care about the surface. So if there is any cancer on the surface of the excised tissue, it means that it is inside the breast. We don't need to penetrate. The penetration became much less important than what do you see on the surface. And that was a game changer for us because terahertz doesn't penetrate much also. Although better than, sometimes in some frequencies better than the optics, but still it is high frequency. I hope this was clear.
No, it totally does. It's the surface that matters because this
the surface that matters, yes.
Yeah, exactly. Okay, so I'll just read this one. It seems the edge of the tissue is always lower in signal in the terahertz imaging. Can you comment on this? Could it obscure the true border of the tumor margin? So essentially how to deal with edges.
So when we receive, for example, a tumor like this one, right, we know exactly maybe I'll put the fresh tissue here. This blue one, remember the tissue is higher than the slide. So this blue one that we see is because the difference in the height between the tissue and the slide. And this is the boundary of the physical boundary of the tissue. What we wanted to look inside and see, can we see the fibrous differentiated from the cancer or not? That's what we wanted to see.
Okay, so there's a surface issue, or a height issue because of the delay associated with that signal.
Right. That's why you see dark blue, because there is edge.
Okay, that makes sense.
Mm-hmm.
So there's actually a question here for this particular slide. What do neoplastic and dysplastic mean for the ducts? Are these difficult to distinguish from cancerous cells in terahertz imaging?
Right. We put here everything the pathologist gave us, healthy ducts, neoplastic duct, and all those, but we will never compete with the pathologist. We're not looking, we do not want to look at exactly what are those neoplastic duct, but because they are there, we put them there. What we wanted to look is the healthy tissue, which is marked as fibrous and fat. So when they remove the healthy tissue, is a mix of fat and the fibrous. The fat is very distinguished. It always appears dark blue because low intensity. The fibrous does not. And as you can see here in this case, it was good because the fibrous and the cancer appeared, one is yellowish and one reddish. But in other cases, we could not see any difference between fibrous and the cancer. So again, we're not competing with pathology. The pathologist can see the cell at the cell like size. We don't want to go there. It's not our goal.
But more of an in-the-loop, fast response, fast
right.
turnaround kind of approach.
The tumor was removed. Any cancer left behind inside, that's what our goal.
That's right.
Right.
Okay, here's another good question. Are your solutions to differentiating between tissue regions leaning more towards signal processing or preparation of the sample before the terahertz examination?
I think, in my opinion, after all the samples we did huge number of samples. I think in the big part on the preparation, but I think now, I think the way we collected the terahertz signal, we have to, because we collected at one, if we are in the reflection mode, we collect this signal in the, it is hybridized polarization between T and TM. So we collect one type of polarization, whatever the system gives us. I think we need to play with the polarization of the signal. I think it may give us more differentiation. We did not do this work yet, and this is something we would like to do. But the statistical signal processing, the classifier is important for the surgeon in the room. The classifier will give him an image saying, this is most likely cancer, this is most likely not cancer. The surgeon will not stand in front of the computer try to interpret the terahertz image. That's where the classifier and the statistical signal processing comes to the game.
Okay, so it sounds like it's still kind of everything could be improved, I guess, is the...
Everything, of course, contributes to the final thing. But I think the measurements, we need to maybe become creative in the measurements.
I got you.
Right.
That's right. Lots of work to be done in the terahertz realm. Okay,
yes,
well,
absolutely.
Thank you, Magda. So, folks, I'm afraid we're out of time. We do still have a number of questions here in the queue, and we'll ask the presenter to follow up with those unanswered questions offline. As we said earlier, this session will be archived on the Society website at mtt.org. All the registrants will get an email reminder with the website address when that's available. For attendees that would like to receive PDH credits, please follow the link in the webcast view and use the code that's provided on the currently shown slide right now, the last slide of the presentation. And once again, I'd like to thank Dr. El-Shinawi for this excellent and informative presentation. We really learned a lot about the use of terahertz with this medical diagnostic approach today. So thank you very much. And also a special thanks to our audience for joining us today. We hope you found today's event valuable and that you'll return for future IEEE Microwave Theory and Techniques Society webcasts. Thank you and have a great day.